arrived at the result that the tangential component of the electrical field is continuous. So the idea was like that. So we have an interface epsilon1, we have an interface epsilon1 and epsilon2. And then the idea is that we have the field just before. So first we have to assign what is the positive, what are the positive directions. Okay. Right. So those are the two big results essentially. On the interface, we apply postulate number 2. We get the result that the tangential components are continuous for the electric field intensity, and the flux density is discontinuous. Of course, this is for the tangential component. For the normal component, we use the polarization equation that gives you the surface charge density at the interface, at the boundary of a medium due to polarization, and that gives us this result. So the flux density is continuous while the field intensity is not continuous. There's a caveat here that sometimes you have to add in the surface charge at the interface. Sometimes that exists, sometimes that happens, right? This interface behavior is the root cause of refraction. We know, I mean, some of you know already, but it's known that light is essentially simply just a wave in EM fields. That's what light is. There are EM fields in space, and then they wave. When they start vibrating, that's what light is, right? And light goes through a phenomenon called refraction. If you have two different materials and light is coming in, light is gonna refract, bend. Those boundary conditions are actually the root cause of this refraction. So let's do an example and show how does that happen. Example. So I have the interface. I have rho S0 per usual. I have this positive direction. I have epsilon1, I have epsilon2. And the idea is that here, just after I have my field, my light wave is coming in. It has electrical fields and magnetic fields. Right now, we only know about electrical fields. So let's just focus on the electrical fields. So I have after the boundary E1, and before the boundary, I have E2. Those are really close to the boundary. I'm drawing them far apart just so that the drawing can be clear. And then we said that E1 can be decomposed into a tangential component, E1t, and E1n. And then E2 can be composed into a tangential component, E2t, and E2n. Now the field, just after the bound, here, just after the boundary, has an angle, call it, actually, let me draw it differently. Let me have this be E1n, and let me have this be E2n. The idea is that I want to put the angle here. I want to have the angle with respect to the normal component. So this is going to be θ1, and this is going to be θ2. This is the angle that the actual field intensity vector varies from the normal components. So what is tan, bless you, what is tan θ1? Tan θ1 is E1t over E1n, right? What is tan θ2? It's a triangle, right? This is a triangle. So tan θ2 is the opposing over the adjacent, right? So it is going to be E2t over E2n, right? What is tan θ1 over tan theta 2, right? That's going to be theta 1 is E1t over E1n dot times tan theta 2 inverted. That's going to be E2n over E2t. Now we know that the tangential components of the field intensity are continuous. So E1t is going to equal E2t. So this cancels, right? E2n and T1n are not continuous, the normal components, but the flux density is continuous. So I need to turn this into a flux density. So this will be D2n over epsilon 2 over D1n over epsilon 2. The flux density, normal component of the flux density is continuous. So those two cancel, become 1, and I end up with tan theta 1 over tan theta 2 equaling, this is epsilon 1, by the way, okay, equaling epsilon 1 over epsilon 2. This famous formula is called Snell's law. And this gives you the angle of refraction, essentially. So if you know theta 1, if you know the incoming angle on a boundary, so you know what the incoming angle is, theta 1, you can easily calculate the outgoing angle, theta 2, from this equation. And it relates to the ratio of the permittivities of the two materials. It's a purely electrical phenomena, and the reason it's a purely electrical phenomena, because light is a purely electromagnetic phenomena, electrical phenomena. Okay? Light is not separate. It's not some. It's not this separate phenomena. Of course, the other kind of interface that we already studied, I just want to review it here, is if medium 1 is some dielectric material, medium 2 is a conductor. What is epsilon for a conductor? There is no polarization. You cannot polarize the conductor. The electrons are freely moving, so any field is going to zip the electrons away. So there is no polarization. There's only free space that still can polarize. So epsilon has to be epsilon naught for a conductor always. Okay. We know we've already solved this for a conductor light. So E2t, E2, and then E1. We said that E1t equals E2t equals 0. Right? The tangential field at the boundary is 0 because you don't have current circulating on the boundary, right? So anyway, we know that the tangential component has to be equal, but furthermore, because this is different material, epsilon 1 and epsilon 0, we know that the tangential component has to be continuous. But there is also an extra constraint we can put in, we have to put in, which is there is no tangential component because current does not flow at the surface of the conductor. Everything is in steady state. So this is the first boundary condition for a conductor. And then we said D1, of course, this applies that D1t equals D2t equals 0. Because we can multiply, sorry, this is bull. What am I writing? D1t, what is D1t? Well, D1t is epsilon 1 E1t, yeah, which is equal 0. Yeah, this is right. So both of D1t and D2t equals 0. Of course, if E is 0, D is 0. The other condition we derived is that E1n, the normal component of the electric field, depends on the charge density, rho s over epsilon 1. So D1n equals rho s. What is E2n? E2n is 0. There is no field inside the conductor. So you established that there is no field inside the conductor. This is an example where a charge density has to arise because all the charges in the conductor lump at the surface, jump to the surface and stick there. So there is a charge density on the surface. Okay. So those are interface conditions. And we have now a theoretical explanation of Snell's law. I think I have to do a summary of what we covered so far. We have developed a bit of theory, but And we are close to finishing electrostatics, because after this, the two concepts that we want to go through are capacitance. And then the final concept is energy. We want to finally show that the electric field has energy. It's not just a mathematical thing that we assume. It is a physical thing that exists in space and that carries energy, just like particles. Okay, so yeah, so the topic of capacitance. So you're familiar with capacitance from circuit theory, really, right? So you've studied this in circuit theory in terms of what's called lumped elements. So circuit theory is really a special case of EM. So there's EM, and the principles of EM lead to circuit theory. But the elements in circuit theory are lumped. Meaning, for example, a resistor in EM. What is a resistor in EM? A resistor in EM is some kind of material, exists in 3D space. It has 3 dimensions. It has structure. Something is happening at every point in space. It's the field equations around it. You have to integrate and blah, blah, blah. While in circuit theory, it's just a symbol. It's just a mathematical symbol. It's lumped. Everything is reduced to some symbol. And the only thing you care about is the relation between the voltage across and the current through. So you only have to relate an across and a through variable of a lumped element. So this sort of thing is called lumping. And lumping does not only apply to electrical components, it can apply to masses. When you solve physical problems with a mass and a spring, and you reduce the mass to just one number m, and the spring to just k, this is called lumping. You don't care about the dimensions of the mass. You don't care about the dimensions of the spring and its construction. You lump everything about the spring into the constant k, and you lump everything about the mass into the constant m. Same thing here. So you're lumping everything about this material into this value R. And then there's an inductance L, and then there's the capacitance. So the capacitance is that you're lumping, you have some kind of configuration in space, you're lumping everything about it into distilling it into one number called C, the capacitance. The question is, how does, in circuit theory, I mean, you don't go into that a lot. You just say, oh, know that V equals IR, just know that. And then V equals L di over dt for an inductor. And then I equals C dV over dt for a capacitor. That's what you care about, the relationship between the current and the voltage, lumped by a certain parameter. Now, how do you get a certain C and a certain L? You might have studied that, hey, you have to design the capacitor this way, or you have to design the inductor this way. But in terms of EM theory, what is capacitance really? Okay. So we have to go back to the relationship between the flux density and the field intensity. So this has units volt per meter, or older units Newton per coulomb. But now, from now on, we're going to stick with volts per meter. So E, we said, is a force field. Is a representation of the field from the perspective of a force field. From perspective, if I have the field and I have then electrons or charges littered around, what forces do those charges feel due to this field? Okay. And then D, Coulomb per meter squared, we said, is a polarization. It is essentially a measure of, hey, I have this space and I have my field. How much does my field polarize the region, the medium? If the medium is free space, I presume that there is dipoles in free space. And how are they polarized? If the medium is material, is wood, the wood has atoms in it. And I'm measuring how does the field, external field, polarize the atom of the wood. So this is what D is a measure of. So there are already an inklings for where capacitors could come in. Capacitance could be a measure of how does the force field polarize the medium, right? How much does it polarize the medium? And already we can see that capacitance has to be something to do with epsilon, because epsilon is a measure of how much polarization you get from the field. So remember we said when we discussed the units of epsilon has units of Coulomb meter squared, right? This is the units of D over the units of E. Let's put the old units, Newton Coulomb. So this equals Coulomb squared over Newton meter squared. And we said we can take the meter out. We have Coulomb squared. And then early on, rather arbitrarily, we said, hey, take this bunch of units and call those farad. Okay. Or we can use our new voltage units, which is Coulomb per meter squared over volt per meter. So this gives me Coulomb over volt, meter cancels meters, becomes meter. And this also is going to be farad. So this equals farad per meter. So notice we already have an inkling that why is this farad? Because this is Coulomb over volt. If you remembered from physics 2, the capacitance is just the charge over the voltage. Okay, we will get there. So what is the farad really? We took this Coulomb over volt and we lumped it into one unit called the farad. But what is the farad really? Right? Seems to indicate something sort of capacity. Right? Meaning that, hey, if I have space, if I have a field, the voltage is an indication of the strength of the field. The more voltage you have between 2 points in space, the stronger the field is. So it seems that it has something to relate charge over voltage. It has something to relate, it relates the amount of charge over the strength of the field. So essentially, depending on how strong the field is, you have stronger voltage. And then this field is going to polarize stuff. And when it polarizes stuff, you'll get more polarization charges. You know, the dipole densities dipole moment has charge times distance. So essentially, you're getting more charging of the space. It's as if you're charging the space, right? So the ratio between the charge due to polarization over the field strength represented in volt is some measure, some indication of the capacity of space to hold charge. So it is advantageous to kind of lump this to get farad per meter. So we get the capacity of space. Really what we're getting is the capacity of space to hold charge per electric strength, per unit electric strength represented in volts. Okay, and that's why for air, epsilon naught is some value. For some material, epsilon is larger than epsilon naught because this material has more dipoles in it, has more charge in it. So it has capacity. You have a capacity to polarize more in the material. So you hold more charge, and more importantly, you hold more energy. Those dipoles are kind of like a bunch of small springs, and you stretch them everywhere. So you're holding more energy in the material due to the same electrical field. Okay. So this is the capacitance in terms of a small element in space, small volume element. So this is how you understand it. It's like if my field, this is my space, this is a small volume element, right? If my field is in this direction, I polarize small volume by constant epsilon, and this represents some sort of capacity. So this is farad per meter essentially. Okay, this represents how much charge I get here from this field strength, essentially how much polarization I get. So this is for a differential element, but also capacitance can be derived more generally, can be extended to an extended. So capacitance makes sense for an extended object too, not just a differential volume element. Okay, so we can have like a charge Q plus, an object that has, you know, two conductors, and there's going to be a voltage between the two conductors, and then there's going to be a Q plus and a Q negative. The idea is that if there is an excess, what happens if I have two conductors? So capacitance, the concept of capacitance can be extended to a three-dimensional big object. One example of such an object is I have two conductors. I have conductor 1 and conductor 2. What happens naturally if I inject some charge in conductor 1? Something must happen, right? What happens is that this charge is going to generate a field. And this field is not just going to stay there. It's going to reach conductor 2. Right? It's going to reach inductor 2, and it's going to induce a surface charge density here, right? So let's say there's let's simplify things, and let's say that there is Q negative here. Okay. So it's going to induce a negative charge density here. So there's going to be a surface charge density, but let's say there is a total negative charge in this conductor, right? What will happen? This conductor will be extended somewhere. It's going to be like a wire. So all the negative charges are going to move across the wire away, right? So we can approximate it by saying there is a positive charge here and a negative charge here. So the capacitance of this extended object, similar to the differential volume, which is just charge over volts. So it's just going to be the total charge over the total voltage between those two objects. So this is the lumped parameter capacitance. This is essentially you have a structure and you get a charge accumulation, and this charge accumulation always comes with the voltage, and the ratio of the Q over V is C. It makes sense to define capacitance this way because it turns out for the structure, it doesn't matter what Q is and what V is. Whatever Q you have here, V will change such that Q over V is always constant. So for whatever structure you have, it turns out that Q, whatever Q is, you inject 5 coulombs or you inject 10 coulombs. Q over V in the structure is always going to be constant. That's why it's useful to define this ratio as a lump parameter. It tells you something about the structure. If Q over V for the structure changed depending on Q and V, it varied. This is not very useful, right? It doesn't tell you anything. It tells you, hey, this ratio depends on Q and V. But because this ratio turns out to be constant and only dependent on the structure, C will only change if you change the structure. So it has information to tell you about the structure. Of course, this is in units of farad. And the information it tells you is capacity, right? Per unit strength, per unit volts, how much charge can you get on those structures? If you get a lot of charge for the same amount of voltage, then you have bigger capacitance. If you get less charge for the same amount of voltage, then you have a smaller capacitance. So let's go and take an example of different structures. Okay, let's say our structure is just a metal ball. Does it make sense to talk about capacitance of a metal ball? So we put some charge on it, right? Yeah, it does, because we have the voltage at infinity. We have V infinity equals 0, right? So this object, we said that all conductors are equipotential. They're going to have an equipotential voltage. So the voltage is the same everywhere. So this is going to have a potential VA, right? And the distance is infinity here, right? So it makes sense to talk about capacitance because we can take the voltage to be with respect to infinity. So in this case, C equals Q, whatever charge we have, over VA. That would be the measure of the capacitance of a single metal object lying in space. What about the situation where we have two metal objects, and then we have plus Q and minus Q? Okay. What you have to do is you have to kind of charge the first object with plus Q and then charge the second object with minus Q. conductors, you cannot create charge. Even if I put just plus Q here and didn't put minus Q here, what will end up is I'm going to have a surface charge density, rho S, right? And then the total charge in the conductor is still going to be 0, right? What happens with capacitors, why is this a good approximation for capacitors, is because when you have a plate, two parallel plates, you have wiring, you have Q plus, although everything is still neutral, you have Q minus surface charge density, right? So you have rho S here, but the total charge density is going to be rho S times the area. And then all the positive charges are going to go down this wire. So you can approximately say you have two objects with Q plus and Q minus. Okay. And then you have VA and VB. What's the capacitance? It's going to be Q magnitude over VB minus VA magnitude. Capacitance has to always be positive, by the way. It doesn't make sense to have negative capacitance. You either have capacity or you don't. Negative capacitor is something that has negative capacity, meaning it without doing anything, it has charge in it, right? And the more voltage you apply to it, the less charge it has. It doesn't make sense, right? So the general formula for capacitance is as follows. So I have two objects. I have a field between them. I have a voltage difference between them, VB, VA. I have Q plus, Q minus. What I can do is I can get the charge by using Gauss's law. This is my surface. So C is going to be the total charge, which is the integration over the Gaussian surface of epsilon E. This is E, the field, dot ds, magnitude, over the voltage from A to B, which is the voltage difference, which is minus integration from A to B, E dot dl, magnitude. Okay, so this is a general formula. Sometimes it's useful. But the method, what is the method for calculating capacitance as general? You have a structure. You either assume V and then find Q and then do Q over V, or you assume Q and then find V and then do Q over V. Okay. So now let's do the most parallel and most famous and most ubiquitous form of capacitance, which is the parallel plate capacitor. In textbooks, when people draw capacitors, they draw them like this, because capacitors are essentially, in practice, synonymous with parallel plates. It makes sense to design capacitors as parallel plates. If you want to get the most capacitance out of a structure, design it as a parallel plate. Capacitance would be the dominant lumped parameter. So parallel plate, it looks something like this. I have surface 1, I have surface 2 underneath it, and the distance is pretty close. The distance has to be pretty close, D. So I have here epsilon. I could have some material. I have the width, I have the length, right? And it could be air. We could have air between the two plates, okay? And then D is much less than L. D is much less than W. Here, we want to do this parallel plate, and we might want to make D small, because now we can apply the infinite plate, charge plate calculation. So the idea is that the top one is going to have a charge density rho S. The bottom plate is going to have a charge density minus rho S. And because the plates are close to each other, you can apply the infinite plane approximation. What does the infinite plane approximation give us? It will give us a uniform field inside. So what will happen if I look sideways, because of the infinite plane approximation, the field is going to be uniform. And it will I'll show you that it's going to only be between the two plates. So two things are going to happen. The field is going to concentrate between the two plates. There won't be any field outside. And the field is going to be uniform. This is the ideal picture. In reality, what will happen is that around the edges, so the field in the middle is going to be uniform, because in the middle, the infinite plane approximation holds, because you're away from the edges. What will happen as you get close to the side, you'll have the field look like this. The field is going to bulge like this. And this happens in practice. The field is going to bulge like this. This sort of bulging on the sides is called fringing. Fringing is not good. Fringing is like a non-ideal phenomena. So the approximation is that the field is uniform. Fringing is a second order effect. So typically we will ignore fringing. So fringing is ignored. Okay. It's a side effect that we want to minimize. People try to figure out a way to minimize fringing always. Okay. What is the field due to infinite plane? So remember, we said that we already derived that actually. So if I have rho s here, I take my Gaussian surface to be this, and then it extends. I'm exaggerating the Gaussian surface, but it looks something like this. And then I have S1, S2. The field due to the sides of the cylinder is 0, because it's going to be parallel to the field. And then I have the field just outside, E1, and the field just under E2. So say rho s is positive. So using Gauss's law, I end up with E1 S1 plus E2 S2 equals rho s S over epsilon. S1 equals S2 equals S, so this cancels, right? And from symmetry, E1 equals E2. There has to be, I mean, you're the equal distance away, so they have to be equal. So 2E equals rho S over epsilon. So the field due to a parallel plate is rho S over 2 epsilon. We derived this before. Above the plate is pointing upwards. Below the plate is pointing downwards. In vector notation, E is going to simply be, so let's introduce a coordinate system here. So this is Z equals 0, and Z is up in this direction. So Z hat is up there. So above the plate where Z is larger than 0, the field is going to be rho S over 2 epsilon naught Z hat. This is for Z larger than 0. And then below the plane is going to be minus rho S over 2 epsilon naught Z hat. This is Z less than 0. What happens if we have a parallel plate now? So this was a single plate. What happens if we have a parallel plate? What can we do? We can do a nifty thing called superposition, right? We can find the field due to one plate and then superimpose it with the field due to the other plate. But one plate has charge rho S, one sphere has charge minus rho S. So what happens outside, we have a field from the plate, which is rho S over 2 epsilon naught Z hat. This is a field from plate 1. Right? But then also we have the field from plate 2, which has a negative charge density, minus rho S. So it's going to be minus rho S Z hat over 2 epsilon naught 0. So above the plate, the field is going to be 0. Below the plate, we have the field due to plate 1, which is, here we are below the plate. So this is going to be minus rho S over 2 epsilon naught Z hat. And then we need to add the field from plate 2, right? So this is from plate 1. So the field from plate 2 is the same. It's below the plate, so it's going to be, but now rho S is negative. So below the plate is going to be negative, but rho S is negative, so the negatives cancels, and then we're going to get up rho S over 2 epsilon naught Z hat. Same thing, the resultant is going to be 0. So from superposition, the field anywhere outside the plates is going to vanish. The only place we're going to have a field is between the plates. Between the plates, the field from plate 1, I'm just here under the plate 1, so it's going to be minus rho S over epsilon naught Z hat, 2 epsilon naught Z hat. Okay, and then I have the field above plate 2. This is plate 1 and plate 2. What's the field above plate 2? It's going to be positive, but the charge density is negative, right? So it's going to be minus rho s over 2 epsilon naught z hat. So the total field inside is going to be minus 2 rho s, 2 cancels with 2, it's going to be minus rho s over 2 z hat. So the magnitude of the field inside is going to be epsilon. Let me write epsilon, not epsilon naught. It's going to be rho s over epsilon. What is the voltage, by the way? The voltage is minus, so this is 0, distance d is the voltage in the plate, from the lower plate to the upper plate. You just do E dot dl, 0 to d. E is constant, right? I can take it out. So E is going to be rho s over epsilon. And then I integrate, this is going to just be d, because here I'm going from, the negative sign cancels with the negative sign, and I'm integrating from 0 to d. So it's going to be just d. Okay. I want to now, I'm ready to write the capacitance, but still I want to relate stuff to the structure. So rho s, what is rho s? Rho s is the total charge of the plate over A. And now I'm ready. Now I can take, so what is C? C is Q over V. What is V? What is 1 over V? 1 over V is A epsilon over D Q. Q cancels with Q. So I end up with a capacitance of a parallel plate being epsilon A over D. This is a very famous equation. Whenever you want to figure out capacitance of the structure, look at the permittivity, look at the surface area, look at the distance. And for a parallel plate, it reduces to this simple form. You might have encountered this in physics 2 or even circuits. So with this, we're out of time. See you guys Monday. Yeah, so this is, I think Monday presentation, we're going to solve some problems on this aspects of this chapter. And then Monday, I'm going to start talking about the energy in the electrical field, which will be the last topic in electrostatics before we can move on to magnetostatics. All right, everyone. Thank you very much for being here, and see you Monday. Bye.